So warm welcome to everybody to our 2022 summer series of Bite-Sized Corrosion. And my name is Vanessa Fisher, and it really is my great pleasure to welcome you and say thank you for joining us for lunch today. We're going to be spending 6 lunchtimes together this season, looking at some of the hidden dangers of cathodic protection. As with all our bite-sized corrosion conversations, we always hope to serve up what we call bite-sized nuggets of information related to corrosion, in the hope that this will make your own corrosion experience easier to digest. So if you're joining us for the first time, you're very welcome. And we do hope that you feel that today and the other sessions in this series are beneficial. Now, having been involved in the cathodic protection space for over 20 years, it's becoming increasingly evident that whilst cathodic protection can be a benefit, there are in fact some hidden dangers as well. And today my guest Neil Webb and I will explore a few of these dangers. Now, Neil really needs no introduction. He's a very familiar face to all of us on Bite-Sized Corrosion. And his cathodic protection experiences over more than 43 years have provided phenomenal teaching moments to me and to many others. So of course, Neil, a warm welcome. It's obvious to say, but cathodic protection requires current. And at the outset, it's easy to say that perhaps the danger from cathodic protection is just the fact that we're playing with electricity.
Well, yes, I think the shock hazard aspect of any electrical device is there, whether it is high voltage or low voltage. And we tend to think that cathodic protection is low voltage. In fact, many people are extremely surprised when we tell them that cathodic protection works in a range of something like 300 millivolts, from minus 850 to minus 1150 millivolts. And that's the operating range. And people are pretty surprised about that. And they say, well, think, how on earth can that cause any issues? It won't even light up an LED. But of course, we've got to get that energy from somewhere. And the usual supply for impressed current systems, which we generally call ICCP systems, is from some utility, either municipal or national, that supplies us power at 230 volts if you're in Europe or Africa, 110 volts if you're in the States. And that voltage itself can be lethal if it is not handled correctly. So for people working on cathodic protection systems who are involved with rectifiers, which take that AC supply and convert it into something low voltage, which is then applied to the pipeline or tank systems, that itself is a hazard. And unfortunately, there have been recorded fatalities, very few, of people working in rectifiers. None in South Africa, but it has happened. One of the challenges with that, of course, is that you cannot test the cathodic protection system when it's switched off. So you have to work on a live system. And therefore, you've got to have personnel who are trained to work on live equipment, just like we have people who operate on these high voltage power lines that are running at up to 400 kV or more sometimes. They don't switch those power lines off, but they have special procedures for accessing them and so on, so that you can have safe working procedures. So yes, shock is a challenge in that specific aspect. And it forms one of the categories of danger that I would call physical dangers. And I think there are 3 categories of danger associated with cathodic protection. And we'll just sketch those out today and delve into them a little bit further as we go through the series. The next category is what one could call the consequential or electrolytic dangers. In other words, what happens as a result of the electrochemical reactions that are associated with cathodic protection. And what is particularly important with that, of course, is the the thing that is just an electrochemical reaction. It's a reaction that is caused by the flow of electric current. And then thirdly, we have what we've called the social dangers. In other words, the dangers associated with people. We're human and we all make mistakes. But the idea is that you don't want to make too many unfortunate mistakes. Let's put it that way.
Sadly, you might not survive if you do. Neil, I think the physical dangers of cathodic protection are a good place to kind of go back to or start. We've spoken about the risk of shock, but that's not the only risk on a plant or a system where there is cathodic protection, because you can draw sparks in other ways as well, which can be problematic.
For sure. I mean, we know that, for example, a motor car has a 12-volt battery system in the car, which is pretty low voltage. And you can touch that without giving yourself a shock. But I wonder how many of you out there are amateur motor mechanics and you've accidentally shorted out the battery of your car. When you've been working on it, you can create quite a nice fireworks display. I remember once working on a car and I accidentally shorted out the battery terminals with my ring on my finger and got a really, really nasty burn as a result. But, how does that happen with CP? Well, impressed current cathodic protection systems can push out quite high currents. And, your intrinsically safe systems, which are developed to prevent arcs and sparks, are very, very low current, way below a conventional CP system. So your conventional CP system, say in a hazardous plant, can cause fairly high inline currents in the pipelines. And if you've got a maintenance operation going and you disconnect a flange or crack a flange, as is mentioned in the jargon, then you can easily draw an arc between the two halves of the pipe when you open that flange. And that has, in fact, caused fires and explosions. And there have even been fatalities, unfortunately, where the two aspects, if it's a cathodically protected pipe, A, you shouldn't be breaking it without having a bond in place. Secondly, the area should have been tested for gas safety before anything is done. And again, so this comes back to what we're going to talk about later on, and that's ignorance.
I think also we need to remember that, for example, the mechanic at the flange has probably no electrical interest and may not know there's a cathodic protection system even installed. And of course, that should go back to your permitting system. And sadly, sometimes those are not as interdepartmental and thorough as they should be. And someone signs it off without necessarily considering all of the ramifications. So it's important that the people who are in those positions of authority in the permitting office have adequate training on what the facilities are on their system and what the ramifications are if they're not handled appropriately, if the CP system isn't turned off when they crack the flanges and so on. Neil, I know that there's also a sort of bizarre, almost hidden danger, and that is when you're trying to weld on a pipeline that is under cathodic protection. That can also be somewhat exciting.
That's actually a two-edged sword, because welding on a pipeline can in fact cause corrosion. But the thing that you're alluding to is that if you were, say, trying to do maintenance on a pipeline where you have to weld a stub into a pipe or cut out a stub and weld in a valve or anything like that, that the inline currents associated with the cathodic protection can in fact interfere with the welding arc. And it makes it very difficult to achieve the weld. Once the pipeline is electrically continuous, it doesn't have any further effect. But it makes your welding operations quite tricky, and you really need to know what you're doing to be able to deal with it. And we've recently had a situation where we've had repeated calls from an operator who was trying to do some maintenance work. say, oh, what can I do? What can I do? What can I do? I can't get my welding operations, particularly when you're dealing with pressure pipelines and coated welding.
There has just been a question that's come in, and let's just go back to the use of flanges, cracking flanges in the presence of cathodic protection. I think just to reiterate, the concern is primarily in the situation where you have a hazardous fluid which could ignite. And then if you're going to crack the flange, you should turn off the CP system for safety. Would you agree?
For sure. But not only that, you should also bond around the flange as an additional precaution. And it doesn't have to be a hazardous fluid in the pipe. It could be a hazardous atmosphere in the area of the pipe. You know, I mean, it might be a water pipeline or a fire water pipeline, for example, in a petrochemical plant. So you've got a hazardous environment, which then has to be declared gas-free before you're doing any hot work. And they would say, well, I'm not doing any hot work. I'm just dismantling a flange. That's just a spanner, not hot work. But the pipeline could be electrically hot.
I hope that adequately addresses the question that was raised. And now let's move on to this, what we've termed consequential and or electrolytic hidden danger within cathodic protection. And one of the challenges is that, particularly with impressed current, we tend to be able to draw quite a lot of current into our system, and that can be problematic when it comes to the coating.
Yeah, I did a paper a couple of years ago at one of the international conferences based on this concept that we know that coating must degrade with time. And most pipelines, in fact, pretty much all pipelines are coated before they are buried. So with time, you need more current from a cathodic protection system. And the title of that paper was, you can't keep turning up the wick. There comes a point where you can no longer achieve anything by pushing more current into the pipeline. Or in fact, we pull the current out of the pipeline, but it's the same concept. And unfortunately, some operators seem to think, my CP is not working, just increase the output of the rectifiers. The net result of that is that you can push the potentials beyond what is called the hydrogen overvoltage potential. And it results, firstly, any cathodic protection system will result in the generation of high pH at the surface. And if you push it far enough, you'll actually generate hydrogen gas, which can damage the coating. But even the high pH and the cathodic reactions can cause blistering of a coating. So you have to have coatings that are resistant to the effects of cathodic protection if you're going to use them on something that is cathodically protected. We had a really graphic illustration of this, 30 years ago, I think it was, where they tried to implement, or they did implement, internal cathodic protection on some cooling water ducts. These cooling water ducts had been epoxy lined, and when we posed the question, is this lining compatible with cathodic protection? Oh yes, it was fully quality controlled, and the surface preparation was perfect, and holiday detection was done, and when they switched the cathodic protection on, the coating came off and blocked the condensers. So
so you literally use the CP to blow the coating off, and that's really not the intention of cathodic protection.
Exactly.
One of the things that you mentioned a little while ago was that under cathodic protection, we can generate hydrogen gas. And one of the challenges with hydrogen gas is that it can cause hydrogen embrittlement of steels. And I think that's a danger that we often ignore and is worth just elaborating on a little here.
Yes, it's important to realize that hydrogen embrittlement really only occurs with high strength steels that are above a certain critical UTS and are stressed to that level. Conventional steels, if we can call them that, and ordinary engineering steels are not susceptible to it. But we do have cathodic protection on concrete structures, for example. These concrete structures may be pre-stressed or post-tensioned, And these pre-stressing components and post-tensioning components are extremely susceptible to hydrogen embrittlement, and therefore one cannot drive a cathodic protection system to the same level as you would on an ordinary steel system. But it really is limited to the high strength materials. So please, guys, don't go running off and panicking. Yeah.
I just want to reiterate that comment just before we proceed is, whilst we want to draw attention to the dangers, we're not asking you to run off, as Neil says, and panic. But as we've alluded to before, and probably we'll get to a little bit later, the more information we have, the better educated we are, the more we understand, the less chance we are to subject ourselves and our assets to these nightmarish conditions. Neil, one of the other challenges that we've dealt with at some length and in slightly different ways is with AC, because we've spent some time in our last series discussing AC corrosion. And of course, interaction with cathodic protection can also be, if we can term it, dangerous.
Yes, at one stage it was felt, and that's before we knew a lot more about it, that you could control AC interference by boosting the cathodic protection system. It's actually turned out with recent research that that is actually the worst possible thing that you can do. Because if you combine AC interference with high levels of cathodic polarization, you can get catastrophic corrosion. And this is particularly problematic when you've got DC interference conditions where you can't control the negative voltages. And that's something I think that we need to delve into a little bit further in one of the later discussions.
Certainly. Another concern, that interaction is kind of from an AC, quote, interference, but the interference with our cathodic protection system from other cathodic protection or other sources of DC can also be a danger when we're talking about CP.
For sure. The interference refers to currents that are flowing in your system that are not as a result of your activity. Depending on which authority you talk to, you get different definitions of interference. But what we need to remember is that any current that is generated, any electrical current that is generated, has to return to its source. It can't disappear. And so if you've got current entering a system from somewhere else, it's going to leave somewhere. If you haven't provided somewhere for it to leave, it's going to leave by itself. And when it does that, it causes corrosion, as we have seen with stray current corrosion. So cathodic protection can cause interference in other structures, and other people's cathodic protection can cause interference on your structures, even if you've got cathodic protection yourself. So that's also a subject that we'll have to take apart in some detail a bit later on.
And Neil, just in light of that, I think we can also consider a kind of interference situation that we cause ourselves. And by that, I mean when our pipeline is not electrically continuous, we've got essentially a mini interference system where we've got current entering and leaving, not where we intended it to flow.
Yeah, for sure. I like to refer to pipeline continuity as the pipeline equivalent of HIV. It's a self-inflicted corrosion situation because you're drawing, and this doesn't matter whether you're talking about impressed current or sacrificial anodes, it doesn't matter where the current is coming from. But if you don't have a continuous, electrically continuous, not hydraulically continuous, electrically continuous pipelines, so spigot and socket pipelines, flanged pipelines, anything where you've got couplings or joints, if you've got current that is flowing in that pipeline and it goes around the joint, in other words, goes from pipe to water and back to pipe, or pipe to soil and back to pipe, you're going to land up with some significant corrosion over a period of time. And we've seen situations where pipelines which were considered to be in non-corrosive areas, just as a result of the long cell action that happens between, for example, clay areas and agricultural areas. these pipelines suffered from significant interference across Viking-Johnson couplings, to the extent that they eventually had to bond them all, find them first, bond them all, and in fact, sometimes cut them out because the corrosion was so bad. And that was after 15 years. So you might say, oh, but here you are, you've had 15 years, what are you worried about? Well, we don't design, as we've said, we don't design pipelines for 15 years, we design them for 50 years. So 15 years to first maintenance is not acceptable. And
that shouldn't be a first maintenance item either.
Yeah.
Neil, just before we move on to the social, we've had a question which I'm not entirely sure I understand, but I'll see if I can elaborate a little. I think the question is, what kind of ranges of high pH are generated in by cathodic protection? And so if we have a high pH soil, is that favorable for the pipeline?
Well, just to give you an example, cathodic protection will re-establish the high pH of concrete, where the pH has been destroyed by carbonation or has been affected by chlorides. So you can generate pH of 12 or 13 on a pipeline surface. Any pH greater than 9 will start to reduce significantly the corrosion rates. And so high pH soils definitely will reduce the corrosion risk of pipelines, yes. And in fact, again, many years ago, one of the well-known CP practitioners in South Africa proposed that they should bed pipelines in fly ash, which actually is a really, really good proposal from an electrochemical point of view, but it was thrown out on the basis of environmental contamination.
Yeah. Neil, in that leads us in quite nicely into the social dangers associated with cathodic protection. And I think that comment that you've made just ties in immediately really nicely. I think one of the biggest dangers to cathodic protection is in fact not knowing or understanding cathodic protection, basic ignorance. Yeah.
I think ignorance is one of the big issues. If you don't know what it is, if you don't know why it's there, if you don't know that it's very, very important to get the polarity right on an impressed current system, you can make some serious mistakes, which are going to compromise the long-term integrity of your system. So ignorance is a huge issue. And I don't mean that in a negative way. I mean, there are some very clever and very well-trained, very experienced people who are ignorant with regard to cathodic protection. Perhaps a better description would be lack of awareness. And of course, that's what this program is all about. We're trying to raise awareness in order to prevent these sort of problems from occurring.
And another challenge with cathodic protection is that it's easy to forget, kind of out of sight, out of mind.
There have been a number of situations where we've actually come across cathodic protection installations, and we phone up the utility and we said, we found this installation on your pipeline, and they say, it's not on our asset register, it doesn't belong to us. It just happens to be connected to their pipeline. Or you come to a rectifier that is so overgrown, you've got to spend half a day hacking it out from the undergrowth before you can even open the cabinet to see if it's working.
And I think related to that ignorance or lack of awareness, but also with this, that it's easy to forget, little things like utility bills for the power supply not being paid will mean that the cathodic protection system is no longer functional, which can result in damage, corrosion damage, that is, to the asset. And just that forgetfulness can lead to very serious damage and possibly horrifically fatalities in a sort of worst case scenario. Neil, there is one other area under social that I think is critical to discuss, and that is vandalism. But I really think we've run out of time today. So I'm going to suggest that we pick this up tomorrow and look at some of the risks associated with vandalism. And in that regard, actually, we're going to be joined by a special guest, Diana Katsky. She's a well-known pipeline design engineer with extensive experience with the upsides and the downsides or the dangers of cathodic protection. So I encourage you to join us for that. But Neil, thank you. I think this has been a valuable discussion. I think it's always a good idea to just air some of the dangers, some of the difficulties. And I hope that everyone who's been with us today has found it in some way beneficial, interesting. You've learned something. Thank you and have a good afternoon.